So this is 2.1.5, classification of particles. Now, I've previously mentioned in another lesson, but again, we didn't dive too deep into that there are two families of particles. And these are hadrons and leptons. So you've got the hadrons. Now the hadrons, you can remember them as the heavy ones. And leptons, and you can remember these are the light ones. So these are the two categories. Now the hadrons can break down into two subcategories, which are baryons and mesons. So baryons, and baryons are made of these things called quarks. So you think about things that you learn throughout education about materials. So you learn that, okay, so materials, some materials are made of multiple atoms, so that's a unit of that material. For example, water, H2O. So one H2O is one unit of water. But then you can break that down. Water is made of hydrogen and oxygen. Then you can break down those atoms, protons and neutrons, and electrons. Then you can break the protons and neutrons down, and you get quarks. Now, quarks don't usually like to exist by themselves, but you can break them down and make them rearrange and become different things. So, baryons are made of these smaller things called quarks. And baryons are made of free quarks. And we'll talk about quarks and their different properties later on. But things like protons and neutrons, they are baryons. They're made of free quarks. Then you have mesons. And we haven't really looked at any mesons yet, but we will do. And these are quark plus an antiquark. So they're not two quarks. That's a misconception that students usually have. They're made of two quarks. It's one quark, one antiquark to make a meson. Not two quarks. You can't have two quarks. And then leptons, which are light ones, these are things like electrons and neutrinos. They are fundamental particles, which means you can't break them down further. So electrons can't be broken down. Protons and neutrons can. Now, I'll make a table where I will put different particles into their different categories in the table. And I'll also start to introduce some new particles which belong to the meson category. I'll also introduce some other particles which are the baryons. And later on, probably not in this lesson, but another lesson, I'm going to teach you how to memorize the quark composition of every single one of those particles. So, let's do hadrons. And leptons. And then for hadrons, we break it down again, and we do baryons and mesons, like that. So for baryons, we got proton, which is P, neutron, which is N. Then you've got the lambda, which is a capital lambda, sigma, And again, I'm going to talk to you guys more about these particles later on. You got the cascade, and you've got the omega. Now there's also the deltas. Plus antiparticles. So you can have anti of all of that. Those will become your antibaryons. Then, for the mesons, you need to know about pions and kaons, which are pi and k. There's different versions of these, and we'll go over them later on. For mesons, you've got electrons, which is E minus. You've got muons, which is mu minus. You've got tau, or sometimes they call them tauons as well, which is tau minus. And you've got neutrinos, which is an electron type, a muon type, and a tau type neutrino, plus their antiparticles. And we close that off. Yep.
You know each one of them. Memorize.
Sorry?
You have to memorize all of them.
Yes. All of them.
So what's the one on the left? Say.
This one,
Yeah.
muon, M-U-O-N-S. And that's the letter muon, mu, like in micro. Yep. For mesons, that one, kaon, K-A-O-N-S. And the symbol is a K.
What's one underneath sigma?
Cascade, C-A-S-C-A-D-E.
So, why is there so many neutrinos?
Because some neutrinos are made through beta emission, some are made through muons, some are made from tau.
Wow.
So different types.
So you see for mesons,
Hmm.
since they're like quark and antiquarks, why don't they just annihilate?
Well, sometimes the quark and antiquark don't correspond to one another. So that's a good question. And actually, some of them do annihilate itself. So, for example, the pi naught, which is the uncharged pion, will have a quark and an antiquark that corresponds to each other. And mesons are usually short-lived particles. They don't exist for very long. So while it comes into existence quickly, it then very quickly annihilates itself and becomes other things. So yes, they also don't like to exist for very long. Yeah? And most of these particles don't like to exist very long. So the most stable particle is really the proton, and then the neutron, and everything else is extremely unstable. Hence why you've never seen an element made of sigma atoms, because they're unstable. So they never really get a chance to exist in real life for very long.
Delta is like, you do use it for change,
Yeah,
like change in height.
yeah, and it's also used for the symbol of that particle called the delta particle. Yeah? Okay, let's start a new page. So, hadrons, these are affected by strong and weak nuclear forces. Now notice I didn't put the electromagnetic force, because not all hadrons are charged. So yes, some hadrons are affected by the electromagnetic force if they're charged, but not all hadrons are charged. So that's not a blanket rule. But all hadrons can experience the strong and the weak. Leptons are only affected, I'm not going to write only because that makes it sound like I'm excluding EMF, electromagnetic force. So I'm going to say that leptons are affected by weak nuclear force. Now again, that doesn't mean that leptons are not affected by the electromagnetic, but not all leptons are charged. So neutrinos, for example, don't experience electromagnetic. And then I'll write down that protons are the most stable particles. Then I'm going to try to explain the weak interaction with an analogy. Now, this is just an analogy. This is not what really happens. But it's an analogy that works really well to explain how the weak interaction works. So let's put weak interaction analogy. So if we have a neutron is kind of like a proton who is holding onto an electron. It's kind of like that. If a proton were to hang onto an electron, overall its charge is 0. Its mass is about the same. So during beta decay, the proton just ejects this electron. So during beta decay, proton ejects the electron. And then it's just become a proton. So for beta plus decay, the neutron that exists is kind of like a proton holding on to a beta particle. Sorry, yeah. So the proton in a beta plus decay would then be a neutron holding on to an electron. Yeah? Sorry, a positron. I'm getting my words mixed up here. Now, we'll talk about quarks and antiquarks very quickly. But before that, I'm going to show you what protons and neutrons are in terms of their quarks. So let's start a new page. We'll put quarks plus antiquarks. So the proton and the neutron. So protons and neutrons are both baryons, which means that they're made of 3 quarks. Now the proton quark structure are 2 ups and a down. So it's up, up, down. The neutron quark structure is up, down, down. They do have different charges. But we're going to talk about their properties later on. For now, just what the quark structures of protons and neutrons and how they discovered that quarks actually exist because you can't isolate a quark by itself. So the first thing is, evidence that quarks exist, is a process called deep inelastic scattering. Which is similar to Rutherford scattering that you learnt at GCSE, where alpha particles were emitted towards a gold foil, and then they scattered when they got close to a nucleus. Now in this case, they accelerated electrons towards these fundamental particles, protons and neutrons. And when the electrons passed through these protons and neutrons, or broke them apart sometimes, then what they saw was that the electrons actually lost some kinetic energy. So there was an inelastic collision happening. Not only that, but the electrons were deflecting from within the protons and neutrons. So if we have a neutron, with its quarks, and we have beams of electrons coming through, so what happened is some of them pass through, some of them deflect, and some of them deflected that way. So the kinetic energies before and after were not the same. Now another thing they did was, by increasing the energy of these electrons and smashing them into these particles fast enough, they could actually break these particles apart. Now you don't just have one proton or one neutron, you've got many of them. And when they smash these particles apart, then suddenly different particles began to emerge that were different from what was there originally. So the explanation was, when these quarks were broken apart, for a very brief moment, they became separated and were no longer particles. But quarks don't like to exist by themselves. So very quickly, they start to grab other quarks, the neighboring quarks, and they reassemble themselves into free quarks again. Now in this process, the particles that started to come back were sometimes different to what was there originally, because they reassembled differently. Also, sometimes brand new, completely new particles were even being created, because some of the quarks were then breaking apart and creating quarks and antiquarks as well. Yeah.
Just like free roaming quarks.
No, free roaming quarks don't exist.
And how they pull different quarks.
When you've broken them apart for a brief moment, the particle don't exist. And very quickly, they reassemble themselves.
They have to be the same particle, right? Because there's only like 3 quarks that drops and 1 down.
No, but through the process of breaking them apart, you could also cause them to create new quarks and antiquarks as well.
Okay.
And then they start reassembling, and they reassemble differently. Right? Now, some of them might even start to reassemble faster than others. And then leftover quarks could decay or become different. So you might even get different particles forming that were different. Yeah? So I'm going to do a simplified diagram of before and after. And if we do our electron beams here, going towards a bunch of particles, so if we do all protons, for example, and then after, what we might get are that some of them reassembled as neutrons. Right, start a new page. So I'm going to do the quark story for beta decay. So first let's write down what we know about beta decay. We've got a neutron decays into a proton plus a beta minus plus an antineutrino. Now I'm going to redraw that with the quarks. So we've got an up and two downs turns into two ups and a down plus a beta minus plus an antineutrino. Then we look at that and we think, well, what's actually changed here? Well, a down has changed into an up. So we rewrite that in terms of the quarks. So for beta decay, it's a down turns into an up plus a beta minus plus an antineutrino. Then we say, okay, let's draw a Feynman diagram of that. So a down turns into an up, decays via the weak interaction, which then creates a W, the beta minus, and the antineutrino. Now notice again, I've drawn the antineutrino going backwards because that's convention in physics. However, the exam board doesn't care about that. So if you draw the antineutrino pointing upwards, that's still fine. Okay? But typically we would draw antiparticles as looking like they're going backwards in time. That's just convention. Now, how can we then make this show the neutron turning into a proton? Well, we've got another down and an up, but these two simply just go up without changing. So that Feynman diagram now shows the beta decay for a neutron turning into a proton in regards to its actual quark structure and how the quarks change. So all three of these together is the neutron, and this is the proton. So we could also do the same for beta plus, but we just have to swap the quarks for the proton turning into a neutron, and a W plus instead of W minus, then a beta plus and a neutrino rather than an antineutrino. And that's the end of 2.1.5.